Okay, so I think that we can start the second part of the presentation. I will start by a section about thread pools. Okay, how many thread pools should we have in our applications? What types of those thread pools should we have? How many numbers of threads in those thread pools? All those kind of questions I would like to try to answer them in this section. Okay, so first of all, I would like to say that many applications out there, including some of my applications, are using Scala's global thread pool as a single thread pool for the whole application. Okay, and those applications are doing completely fine, and those companies are doing completely fine. And why is that? What is the reason of that? The reason is that, let's be honest, not every application out there, including many of my applications, don't require high performance, high throughput, low latency, all those rigorous performance requirements. So a single Scala's global thread pool for the whole application will do completely fine in such cases. And on the other hand, if you have some rigorous performance requirements in your application, then such a single Scala's global thread pool might not fit the problem, might not be the solution to your problem. Okay, in such cases, a good rule of thumb is to use at least 3 different thread pools. Okay, so we'll have a different thread pool for CPU bound operations, you will have a different thread pool for blocking IO operations, and you will have a different thread pool for non-blocking operations. This way, different types of operations with different characteristics in the runtime will not interfere with each other. They will be scheduled by completely different thread pools, so they will not get into the way of the other computation. Okay, we will have like a complete separation of them, and that's a good thing because they have different characteristics, so they should be like separated from one another. Okay, when it comes to concrete types of thread pools that might be used in such cases, in the first scenario, in case of global single pool, in case of Scala, it's probably the global Scala's thread pool, which under the hood will be backed by a fork join pool, which is a very good general purpose thread pool. It will work well if you are mixing different types of computations on that single shared thread pool. Okay, so it will work well if you are mixing, for example, CPU bound operations with blocking IO operations on the exactly same thread pool. In the second scenario, where you have separate thread pools, it depends on the characteristics of particular computation. So if it's a CPU bound operation, it depends on the number of tasks you have and the time it takes to process a single task. So in case you have many small tasks, by small I mean short running, then you should beware of thread contention. If you, for example, have a thread pool with a single queue before or in front of the thread pool, you might encounter thread contention in such cases. Okay, because basically you will have many small tasks waiting in the queue, in a single shared queue, and many threads will contend over that single shared queue. So you will pay the price just for the contention. You will pay the price for the overhead. In such cases, for example, fork join pool might be useful because fork join pool, first of all, uses multiple queues under the hood, and second of all, it also employs work stealing, which means that one thread might be taking tasks from queues of other threads. Okay. On the other hand, if your computations are long running, then you should be careful with using fork join pool, because in such cases, when you have a long running CPU bound operation, it's possible that the fork join pool will think that you are performing a blocking IO operation, which is obviously not true. But in reaction to that, fork join pool will add more threads to that thread pool. And as I said, for throughput sensitive applications, it's optimal to have the same number of threads as you have a number of CPU cores in your hardware. So if you will have significantly more threads in the thread pool than you have CPU cores in your hardware, then you will decrease the throughput of such applications. In such cases, a bounded pool with an upper limit of the size will be helpful. Of course, sometimes you will have a problem, or you might worry which one should you pick, because your application, your use case might not be might be specific one. In such cases, of course, try to benchmark, try to use different configurations, different thread pools, and try to answer your question during a benchmark. Sometimes it's possible that the benchmark will be hard to express and to express your real production scenarios in those benchmarks. You could, for example, use here multiple deployments of the same version of the same application with multiple versions of that applications. You could, for example, use canary deployments here, and you could have many different instances of your application. Some will be using one type of a thread pool, the other will use a different type of the thread pool, and you will see in the runtime, in the production environment, which pool behaves better. You will see that through monitoring, through metrics, and all of that. And this might answer you the question, what type of a thread pool should I use? How many threads should I have in such cases? Okay, when it comes to blocking I/O operations, a good rule of thumb is to have an unbounded pool. This might sound scary, this might sound dangerous, but in the next slide, I will show you that it doesn't have to be scary and that it has a couple of benefits. Instead of bounding the pool at the level of the thread pool itself, we will provide limits or bounds at the higher semantic level, but we'll get to that in a moment. And when it comes to non-blocking I/O operations, a single small bounded pool should be completely fine. In such cases, one or two threads should work completely fine, and that pool should be used only as a dispatcher. Okay, so it will work basically as an event loop, and it will only wait for the notifications coming from the operating system, notifications about the result of the I/O operation. And as soon as the notification from the operation system arrives, you should immediately shift your processing to one of those other two thread pools. Okay, so either CPU bound one or the one for blocking I/O. Depends on what operation happens after your non-blocking call. Okay, basically you shouldn't be performing any computations or blocking I/O operations on that pool which is supposed to perform or await non-blocking notifications. Okay, so as I said, a good rule of thumb for blocking I/O operations is to have an unbounded pool. Okay, so let's imagine that we have three types of blocking I/O operations in our application. We have blocking network calls, we have blocking database calls, and we have blocking file system operations. Okay, and under the hood, all of them we will use a single shared cached thread pool. Okay, the cached thread pool is unbounded one, which means that we will not have any limit, at least not at the level of the thread pool itself. Okay, instead we will provide those limits at the higher semantic level. So for example, we will provide those limits in the clients to the external subsystems. For example, in case of HTTP communication, we might provide such limit in the configuration of the client itself. We might say that, okay, we would like to have at most 50 simultaneous HTTP connections. Okay, if the library you're using for some external subsystems doesn't allow you to easily limit the number of simultaneous operations, this might also be solved really easily. You could, for example, use a semaphore from Cat's Effect, a semaphore which, by the way, is a non-blocking implementation of a semaphore because it uses fibers under the hood, and semaphore will allow you to limit the number of external calls to some subsystem. Okay, so what did we gain by providing those limits at the higher level and not providing them at the level below? The first thing is that effectively we have limited the size of the thread pool to 80. Okay, at least in this particular example. Okay, So we have a limit of 80. The benefit is that we didn't have to think about that number 80. Okay, at no point in the process we had to think or calculate the exact number that should be bounding the thread pool itself. Instead, we were thinking only in those high level, fine-grained limits. Okay, so we were thinking of how to limit network calls, how to limit database calls, and how to limit file-based operations. And in effect, this resulted in a global limit for that pool. Okay, this is the first benefit. And the second benefit is that the pool is cached, okay, and reused by many different types of computations. Okay, what does it mean that it's cached? It means that when the thread is finishing its execution, it's not killed immediately. Okay, so it will remain in the thread pool for quite some time. By default, cached thread pool will leave the thread in the thread pool for 60 seconds. What does it mean? It means that if the thread finishes its blocking network call, for example, it might be immediately reused for a blocking database operation using JDBC, for example. Okay. In effect, instead of like constantly healing and creating new threads, we are reusing them. Okay, we will have less overhead. We will pay less price for thread management, context switches, thread creation, and all of that. Okay. Yeah. So in the previous section, I started talking about like good practices and good rule of thumbs in terms of in the world of thread pools mostly. I would like to continue with those good practices, but in concurrency world or multi-threaded world in general. Okay, so the first practice would be avoid concurrency for as long as possible. Okay, the concurrency is hard. Okay, and this is the main reason. So if you have two solutions to your problem and both solutions work and satisfy you, then in general you should pick and one of them uses concurrency and the other doesn't, then in general you should pick the one that doesn't use concurrency. In the long term, it should be easier to maintain, less error prone, easier to reason about as well. So basically we are applying principle of least power here. Okay. The same goes with low-level and high-level concurrency. If we have two solutions to our problem and both satisfy you and work well for you, and one of them uses low-level concurrency and the other uses high-level concurrency, in general, you should also pick the high-level solution, because here as well, the high-level solution should, in general, be easier to maintain long-term, easier to reason about. For example, it might hide some implementation details that would otherwise be visible with the low-level implementation. And in general, this should be less error prone. Okay, so also principle of least power applied here as well. Okay. The next thing is that you should choose your concurrency primitives very carefully. We have many different concurrency primitives in the modern software development, in the JVM world as well. And there is a reason for that. Each concurrency primitive addresses or solves a different set of problems, okay? Which means that you don't have to use a single concurrency primitive for every problem or for every concurrency problem you have in your application. And unfortunately, we have a problem in Scala ecosystem with that. Unfortunately, we have a problem of overusing ECA actors, okay? So first of all, ECA as a library is a great library, very performant, very reliable, already very mature, okay? Actors on its own also are a great concurrency primitives. Some problems are solved by actors really well and in an elegant way, but that doesn't mean you have to use actors for every concurrency problem you have, okay? Also, you don't have to use ECA actors to organize your whole application. Unfortunately, I have seen such applications. Well, basically, ECA actors or ECA in general was used as a framework for the rest of the application, for the whole application. And in my experience, this doesn't work well. Okay, the next thing is that you should know the thread pools you have in your applications. You should know your thread pools. You should know thread pools that are created by the external libraries or are used by the external libraries, because at the end you are responsible for your application in the production and not someone else, right? You should be confident with how your application behaves in production. You should also aim for the application to be predictable. Okay, so you will know how it will behave depending on different different scenarios in the real world traffic your application gets. Okay, and I will show you an example of that. Very long time ago, I was performing some communication with many microservices in my company, and I wrote a single piece of code that would like communicate with them. Okay, for this purpose, I have used OKHTTP, which is a blocking client for HTTP calls, and I said in the configuration that I would like to have at most 100 simultaneous connections. Okay, and my assumption was that in the runtime I will have at most 100 threads created solely for the HTTP communication. Unfortunately, to my surprise, in the runtime I got 134 threads. Spoiler alert: 14 are completely unrelated to the HTTP communication, but it still left me with 120. Okay, which was surprising to me. Moreover, the number wasn't deterministic. Okay, sometimes it was 120, sometimes 125, sometimes 115. So basically, I lost predictability of my application. I wasn't sure how this application will behave. For example, if there's a spike in the load on the application. Okay, I lost predictability. I lost confidence. I wasn't sure whether I could deploy the application in the production. Okay. Moreover, I wasn't able to find the reason of that in the code or in the documentation of OKHTTP. Okay, so there was no answer. At least I wasn't able to find it. Okay, so you should be careful. You should know that how will your application behave when bad things start to happen. Okay, the next practice is basically the result of the previous one. Okay, so if you are using some external library and that library creates some thread pools or requires some thread pools for its runtime, then you should in general prefer the libraries that allow you to plug your own thread pools inside the runtime of that application. Okay, and there are many benefits of that. First of all, you are in the full control of a thread pool. Then you might configure things like the upper bound of how many threads might be created by the thread pool. Also, you can provide your own implementation of the queue. You might also provide your own limits for the size of the queue, which is also recommended to provide limits for the queues in the thread pools you're using. Also, you might apply metrics or monitoring on both the thread pool itself and the queue of the thread pool itself. Okay, so many benefits of using your own thread pools and plugging them into some external library. Sometimes those libraries will not allow you to provide your own, but at least they will allow you to configure extensively the characteristics or the details about the thread pool, the queue, and all of that. Okay, so in such cases, it's still fine to use those libraries. Okay, if they allow you to have a full control over the runtime execution, basically. And fortunately, I was able to do so in my scenario, in my use case. I was able to create my own custom thread pool when I said that I would like to have at most 100 threads simultaneously. I plugged it into the internals of the OKHTTP, and as expected, in the runtime, there were 114 threads. 14, as I said, were completely unrelated to the problem I was solving, and 100 was used solely for the purpose of HTTP communication. So basically, I was confident that my application will behave fine. Okay, I regained confidence. I also regained predictability of the application. I wasn't worried that during some spike in the load, my application will behave badly. At least this wasn't the reason. Okay, in such cases, of course, there are many other possible reasons that things get wrong in your application when something that happens. Okay, the next thing is that if you are if you have some rigorous performance requirements for your application, then you should decide whether you optimize your application for fairness or for throughput, because depending on that, you might be using slightly different types of thread pools, slightly different configurations. So for example, fork join pool itself is optimized for fairness. And this is basically, the reason is that is the one I already told you, that it will add more threads if there's a high load on the thread pool. The second reason, the second example is that fork join pool is very often used as a Scala's global thread pool. So in combination with Scala's futures, and Scala's futures are also optimized for fairness. So by default, many applications in Scala are optimized for fairness, which is perfectly fine, okay? Which is perfectly fine. But sometimes you will require throughput from your application, and then you might need to change those default semantics. Okay. In such throughput sensitive applications, as I said, it's good to have as many threads in your thread pool as many CPU cores you have in your hardware. Okay, this will be the optimal number. Okay. The next thing is that if you are using this expression in your code, and definitely, especially specifically if you are using some older JDK versions, then you should be careful. Okay, so the expression is runtime.get runtime.available processors, and this expression, especially on the older versions of the JDK, are not 100% reliable when it comes to virtualized environments. So it's possible that you are running your application in a container, you deploy that application on some hardware, and if the hardware has 4 cores, for example, it's possible that the expression returns 1. Okay, which is obviously not the case, this way you will be underutilizing the hardware you have available for your application. Okay, so I will show you in a moment how we can protect against that. Okay, in the newer versions of the JDK, many problems related to that were solved, but it's still possible that for whatever the reason is, the exact number will not be correct. Okay. By the way, the lowest number that might be returned by the expression is 1. Okay. So in the worst case scenario, you will get 1 by the expression. Even if 1 is the correct answer because your hardware has only 1 CPU core, then it's risky to have a thread pool with a single thread only, especially if you are trying or you are attempting or planning to block on that thread pool, because blocking on a single on a thread pool with a single thread might lead to some trivial deadlocks. Okay, and how can we protect against it? Well, basically, we have to make sure that whatever is returned by the expression, it will be guarded by some outer expression. And in this case, I'm just making sure that regardless of what the expression returns, I will have at least number 4 at the result of the expression. So in my case, I will have at least 4 threads in the thread pool I'm creating. Okay, and the correct number, that 4, the correct number will depend on your environment, basically. Okay, so this is all when it comes to like good practices, best practices, and good rule of thumbs. Now I would like to jump into the world of asynchronous stack traces. But why do we even have to care about asynchronous stack traces in the first place? What is the problem with asynchronous stack traces? Let's see an example of that. Let's see an example of a very simple application where we have some main method which awaits for the execution of asynchronous computation. That asynchronous computation on its own is performing some logic and is calling sequentially another asynchronous computation. And that another asynchronous computation fails with whatever the reason is. This is an illegal argument exception in this case. And what exception, what stack trace will we get in the main method? Okay, the stack trace is as follows. It's a pretty standard regular stack trace you would get in a Scala application. So a couple of things worth noting here. The exception is correct, like it's illegal argument exception. The message is also correct, so it's a test exception. Method bar is there, which is fine, which is also correct. And unfortunately, there's one thing missing here, okay? And the thing that is missing here is method foo, okay? Nowhere in this stack trace you can find method foo, okay? Which is a problem. We've lost some valuable information that might be really useful when debugging the application. Foo method was definitely used in the asynchronous processing. Moreover, it was basically the beginning of the asynchronous processing. It was the first step of our asynchronous flow. Okay, so we've lost very important piece of information, even though our application is like the simplest possible one. So you can imagine how many informations are lost when we have a complex asynchronous flows, asynchronous processing in our production applications. Can we do something about it? There are a couple of attempts to that problem. Not only on Scala, of course. So some attempts try to solve the problem at the level of stream processing library. This is what happens in Project Reactor, for example. Kotlin tries to solve the problem at the level of coroutines. Coroutines are like an extension to the compiler. We also have a solution in IDE. In this case, it's a solution in IntelliJ. And in the Scala ecosystem, we have a couple of attempts of solving asynchronous stack traces. We have a solution in Zio. Recently, we got a solution in Cats Effect, and very soon there will be a solution to asynchronous stack traces in Monix. The pull request is already opened, and the person who is responsible for that is Piotr Gavryś, who was presenting today. So the pull request is open. And I think it's a matter of a couple of days or weeks, maybe, before Monix has asynchronous stack traces as well. Okay, and now I'd like to show you an example using Cats Effect. How will the stack trace look like with those solutions applied to the problem? Okay, so basically we take the exact same application we had, the simplest possible one. As you can see, just by looking at the shape of the code, it's like almost the same code. The only thing that changed is that I've replaced Scala's future with Cats Effect IO. Okay, this is like the only change, like in general. What exception do we get here? The exception is as follows. The exception is pretty standard one. A couple of things worth mentioning here. The exception is correct, like it's illegal argument exception. The message is correct, it's test exception. Bar method is there, and unfortunately, foo method is not there again. Okay, so we've also lost a valuable, an important piece of information, basically the information about how the asynchronous processing really started. However, it turns out that the stack trace you see comes from Cats Effect 2.1, which is not the latest version of Cats Effect. The latest version is Cats Effect 2.2, and asynchronous stack traces were introduced in Cats Effect 2.2. And how will the stack trace look there, or already looks there, because it's released. Okay, so this is the stack trace. This is the stack trace I got in Cats Effect 2.2, and there are many things. There are many interesting things in this stack trace. First of all, the exception is correct. It's illegal argument exception. The message is correct. Method bar is there, and method foo is finally here. We finally have that piece of valuable information in this stack trace. Okay, we finally can try to debug our application. We can reason about how the asynchronous processing really looked like just by looking at the stack trace we got. Also, we've got rid of some noise related to the stack trace. Basically, we have no information about like the internals of the Cats Effect IO data type and its run loop that is running under the hood. We also don't have like noise related to calling JDK internals, okay? So that the noise is removed. The question is, how does it work? How is it possible to have such stack traces? Well, it turns out that the Katz effect IO data type is in full control of its own execution. So if you have a bunch of small IO expressions and you combine those small IO expressions into a bigger one using some combinators, then you execute the bigger IO expression, then the Katz effect internals, its internal run loop, is fully aware of every step you have in that bigger expression. And by executing those, the bigger expression step by step, it might use that information. It might use that information about particular step to recreate the correct stack trace of asynchronous processing that takes place. Okay, so basically during the execution, the internals of Katz effect will try to work out what the actual execution flow is. Okay, and in the process, Katz effect internals will be also able to remove the noise related to the internals of the run loop itself, and internals related to JDK calls as well. And we finish with a very precise, very short, very informative stack trace at the end. And in the last section of my presentation, I would like to talk about application architecture and also application structure. And the structure is something I would like to start with. Okay, so when it comes to structuring asynchronous Scala applications, we have many different approaches, many different flavors to do so. For example, some applications are completely organized around Scala's future. Scala's future is a part of the standard library, so it's very easy to organize your whole application around it. And that approach is completely fine. I even have some applications that are still using Scala's future for the whole application. Some applications, as I said, are organized completely over ECA actors, which, as I said, in my experience, doesn't work that well, because ECA actors are like concurrency primitives. ECA itself is a toolkit, so I wouldn't be necessarily using ECA as a framework for your whole application. And unfortunately, I have seen such applications. Okay, some applications are also organized around some concrete IO monads, like Katz effect IO, Monix task, or Zio. So everywhere in the code, basically, you will have a concrete data type. And it's also very popular approach. I also have some applications that are doing this style. Also, we have one of the approaches we have are free monads. Free monads are not that popular anymore in Scala as they used to be. But first of all, there are still many valid use cases for free monads. And second of all, there are many applications that already are using free monads. So why bother with refactoring them or completely re-implementing them with a new approach? Okay, and also we have a solution that is popular, especially in the world of pure functional programming, which is tagless final encoding. There are also many other approaches and many other flavors, and I will also show you what is my approach. My approach is basically like a combination of two approaches from this particular list, but we'll get to that. Now I would like to compare those types of structuring your application, your asynchronous Scala application, to modern application architectures that we have in software development. Okay, so how does it compare? How the list compares to modern application architectures that we have in software development? Okay, so what application architectures do we have in nowadays? Okay, so we have a couple of them, at least a couple of them. We have things like hexagonal architecture, we have ports and adapters, we have clean architecture, we have on-your architecture, and possibly other as well. We will not compare them, we will not go into details about them, because the idea behind them is exactly the same. The idea is exactly the same. They differ only in implementation details. So what is the idea behind them? Well, the idea is that the center of your application should be the domain model, domain logic, business logic. This should be the core of your application. And anything else like infrastructure, like tests, like logging, like external communication, all of that should adapt to the domain, to the business logic, and not the other way around. Domain logic should be completely free of knowing anything about infrastructure, about tests, about logging, about externals, all of that, okay? Do we have a name for such property? It turns out that we have such a name, and the name comes from object-oriented programming. The name of such property is dependency inversion principle. It's a very old principle that comes from around mid-90s, which was created by object-oriented developers in the object-oriented world, but the principle is so general that it might be definitely used for functional applications as well, and I think it's worth doing so. Okay, so there are two rules behind the dependency inversion principle. The first one states that high-level modules should not depend on low-level modules. Instead, both of them should depend on abstractions. And the second rule states that abstractions should not depend on implementation details. Implementation details should depend on abstractions. Okay, so how does the inversion principle compare with those approaches of structuring your Scala application? Let's see at a first approach. The first approach is to use a concrete data type all over your application. You will have a concrete data type basically in every place of your application. So in the domain layer, in the abstractions, in the interfaces, in the components that are using those abstractions, you will have a concrete data type. In this case, it's Monix task. In the infrastructure, you will also have a concrete data type, and in the tests as well. So basically, a whole application is organized around single concrete I/O monad. But there's a question, how does it compare to dependency inversion principle? Well, some people might argue that it's not compliant with dependency inversion principle because our abstractions know some implementation details. In this case, our abstraction know that, for example, they might be executed asynchronously, okay? So some people might argue that it's not compliant with dependency inversion principle. Let's assume that those people are correct, okay? How can we free our domain logic, business logic, out of knowing such implementation details? Of course, the first approach that comes to mind is tagless final encoding. So our domain will not use a concrete data type, but a generic context instead, and we will work, instead of using a concrete data type, we will work in, we will be expressing our logic in terms of capabilities and not concrete data types, okay? So in the domain, we have tagless final, and also in the infrastructure, we are having tagless final. Of course, in tests, we can no longer use the tagless final. We have to interpret the tagless final algebra. However, there is a problem with that solution, and there are two main problems with that. The first one is that sometimes it might be hard or challenging to express your infrastructure code in terms of tagless final encoding, and for example, in terms of Katz effect type class hierarchy. Okay, especially this might be hard if you are using some legacy Java APIs or some awkward APIs in general. Okay, the second problem is that often you will work with people who are, for example, new to Scala or new to functional programming or new to programming like professional software development in general, because they will be starting their software development journey. And for those people, expressing the infrastructure code in terms of like capabilities and type class hierarchy from Katz effect might be challenging, okay? Might be challenging. So can we do something about it? I think that we can do something about it. This is the approach I'm using. So basically, I'm using a combination of those two approaches I have shown you, and I'm taking the best of both worlds, actually. Okay. So in the domain layer, I have tagless final approach. My business logic, my domain logic is completely free of any implementation details. Moreover, since it's the domain layer, I don't have to use any type class stronger than monad or monad error. Okay, I don't have to use things like async, concurrent, sync, effect, and all of that from type class cuts effect type class hierarchy, because all of them belong to the infrastructure. And here in the domain, they are represented as abstractions, and abstractions are free of knowing those capabilities. Okay, so this is the first thing. And in the infrastructure layer, where I already have many implementation details, for example, the name of the class is already like shouting out loud the name of the database I'm using, so one of the implementation details. In such cases, when I already have many implementation details in the implementation, I don't have to worry about adding another implementation detail on top of that, which in this case is a concrete IO monad, Monix task in this particular example. Okay, so in the domain, tagless final, in the infrastructure, concrete data type, which is much less challenging in such cases I have described to you, to express your infrastructure code in terms of concrete data type instead of like type class hierarchy for cuts effect. And also in test, I'm using a concrete data type as well. One thing that is worth mentioning here, notice that I'm not using ID monad in tests, and there's a reason for that. ID monad itself is an eagerly evaluated data structure, while probably, at least in this case, I'm interpreting my tagless final algebras into lazily evaluated data structure. So I would have different evaluation strategy in tests and in the production code. And this is only asking for problems. So unless you are interpreting your tagless final algebras into future, which is not popular, let's be honest, then you shouldn't be using ID monad in such cases. Okay. Yeah, and this is all I have for today. If you have any questions, feel free to ask them. You can also try to catch me after the conference, and if I'll know the answer to your problem, I will be more than happy to help. Thank you.
はい、パウエル・ユルチェンコさん、発表ありがとうございました。時間の関係上、質問は懇親会などにてお願いいたします。以上をもちまして、このセッションを終了いたします。ご視聴いただきありがとうございました。Thank you, Paweł Jurczenko.
Thank you. Thank you.